Imagine a scarce resource that can help solve global warming, enables medical imaging, and enhances national security with a price up to $20,000 per gram. And we're running out. You just imagined Helium 3. After 9/11, the Department of Homeland Security used most of the Helium 3 reserves to produce neutron detection devices, which they placed around the United States. Helium 3 is also used for nuclear fusion energy, which once commercialized can supply a sustainable and renewable energy source for all of humanity. If you inhale Helium 3, it can also be used to treat respiratory diseases, including asthma. It also enables the MRI scanner to get extremely high resolution imagery of the lungs. It can also be used for the cooling of supercomputers, and this could also be used for the cooling of battery storage systems. On Earth, there are no natural reserves or resources of Helium 3. The way that it's produced is with tritium, which is a waste product of nuclear weapon production. There is estimated around 27 kilograms on Earth, which is not a lot. It will run out. The sun produces Helium 3 and it's transported through solar winds. Because the Earth has a magnetic field and a strong atmosphere, it repels it. The Moon, however, doesn't have this, which allows the Helium 3 to be deposited into the regolith, and that has been happening for billions of years. In our process of producing Helium 3, we also produce water. As you're aware, water is required to sustain life on Earth as well as it will be in space. It is estimated that the cost to transport water from the Earth to the lunar surface is $30,000 per litre, or a quarter of a gallon. And it's also estimated that by 2030, the demand will increase to 16,000 tonnes. The mission of space industries is to extract and supply resources on the Moon and provide the Earth with Helium 3 in an environmentally friendly method. In order to identify a viable and commercial resource for a commercial business model, our geologist Richard Hall has compiled an indicative resource estimation which has identified several high-grade targets for our first mission. In order to extract that resource, we have produced a lunar processing system. This includes two vehicles, of which one is an extraction vehicle and one is a processing vehicle. The resource extraction vehicle is predominantly designed to produce water and Helium 3, and in that process produces other isotopes which can be used for breathable atmosphere. The demonstration vehicle will have an extraction rate of approximately 6.5 tonnes per hour and a life cycle of 5 years with zero maintenance. The demonstration vehicle will predominantly be designed to produce water and to demonstrate the production of Helium 3. The first step for producing the resource on the lunar surface for water is to heat the regolith to 250 degrees to extract the bonded water. At 850 degrees temperature, we extract the Helium 3 as well as the other isotopes. These are then collected in the stage 1 processing system, which using temperature and pressure, we can extract the water from the Helium 3. These are then stored in the onboard storage of the Lunar Resource Extraction Vehicle. The vehicle then transports back to the Lunar Processing Lander, where it deposits the resource into the stage 2 processing system. This system, using a membrane technology instead of cryogenics, can separate the resources into usable products. The Helium 3 is then deposited into a mineral return vehicle and extracted back to Earth for consumption there. The Lunar Processing Lander, the first task is to land safely on the Moon and deploy the resource extraction vehicle. Once this has been completed, the processing lander then becomes the resource processing and communication system. On the first mission, we're also estimating that we'll have a 1 to 3 tonnes of additional payload space for scientific purposes. The team that's making this possible are experts in all of their fields. We currently have 12 members, and that's rapidly expanding. My background is in mining and resources here on Earth, and we operate mostly in remote operations in Australia, as well as remote operations in the jungles of Africa. Speaking of remote operations, Sam Forbes is a remote operations specialist. He works as a general manager for Fugro in Australia, doing deep sea operations, which use high latency, similar to space. In regards to space, our advisor, Dr. Gordon Rosler, who formed Space Department for Robotics in Space for DARPA. He is now the President of Robotics in Space. We also have legal commercial space law, who is Donna Lawler, and she is well known internationally. Other than our team, we're also collaborating with companies with space heritage. We're in discussions with Jacobs, who are actively supporting companies within the space industry in Australia, and we're discussing with them verification, validation, and testing. We've signed a strategic intent with Maxon, who have commenced the development of our Lunar resource extraction vehicles' drive systems. We've also signed a strategic intent with Fugro, who are working with us to develop the remote operations for our vehicle. We have been supplied design software by Dassault Systems, which has enabled us to rapidly design our vehicles. We are also a part of the Australian Remote Operations for Space and Earth, which is a remote operations institute in Australia dedicated at connecting mining leaders with space leading companies for technology transfer. Space Industries is looking for more partners with space heritage to help us meet our targets. We are also looking for offtakes for the future supply of water in space, as well as Helium III here on Earth. These offtake funds would be used for the development of the project. We're also self-funded and supported by the in-kind support of our team, and as we are rapidly progressing with the development, we are looking for funding opportunities. As mentioned, we have commenced the development of our lunar resource extraction vehicle, and we have rapidly progressed with TRL 3, and we are now progressing onto TRL 4, which is our lab prototype. We are estimating to have the first lab prototype completed by Q4 2020, and the overall objective is to have a commercial resource extraction vehicle on the moon by 2024, in line with the Artemis missions. The Helium III market currently has a demand of around 100,000 litres. The problem here is that the supply to the market is restricted to 14,000 litres per year. 10,000 litres per year is for the United States market and 4,000 litres per year to the international markets. This is because of the depletion of the reserves, and the US government has decided to build those stockpiles up again. This presents a market with no competition for 75% of that market, which is estimated at $2.4 billion annually. The other market that we can capture is the space water market. Currently, there's a demand of roughly 244 tonnes, and this is expected, as mentioned, to go to 16,000 tonnes by 2030, producing a market of roughly $160 billion with 0 competitors. Reaching 16,000 tonnes also would require 300 launches per year at 5 tonnes payload, which is more than the entire world's capability for launches at the moment. By producing Helium 3 and returning this to Earth, we are enabling the development of a truly sustainable and renewable energy source, which is nuclear fusion. The water that we produce in space can be used for propellants, agriculture, and also provides an efficient space transport mechanism. The water can be used to enable multi-use landers, and with the upcoming Artemis missions and a lot of infrastructure transported to and from the moon, it's much better and efficient to have a multi-use vehicle. The water can also be used to enable multi-use orbitals for thrust for the International Space Station, satellites, and the Gateway. The cost benefits are significant for refueling in space. We estimate the development of our lunar resource vehicle to be $50 million, which would enable us to supply water in space for as low as $10,000 per litre. A lander currently has a range of $30 million to $300 million as the cost. With a fuel capacity of 400 litres, would be able to be refueled for as low as $4 million. A satellite costing $50 million to $500 million with a propellant tank of 20 litres would be able to be refueled for as low as $200,000. These are significant cost benefits. Space industries are making resources in space a commercial business opportunity in line with the Artemis missions and will benefit all humanity. Thank you for listening.
I was really interested in the fact that you've identified a market for Helium 3 that's not nuclear fusion. I mean, nuclear fusion is great, except it doesn't exist. And I think that Helium 3 fusion is a lot hotter than normal, like deuterium or something like that. So I applaud you for identifying the other market, and especially the MRI one, which I thought was great. Do you think that that with launch costs potentially coming down precipitously in the near future, a la Elon and others, that this would impact your business plan, but also provide new opportunities to you?
I think it can produce both. It's tough to say. At the moment, the amount of launches out of the United States is limited, so that'll have a major factor. The number of sites for orbital launch is limited, so I think it'll be quite a significant amount of time before the number of launches can be enough to sustain the demand for water in space.
So we know that there is now water on the moon, but we don't really know the depth or the form that the water's in. How does that going to affect your plans for extracting it?
Yep, so there's two sources that we can target. So we can target the bonded water, which is bonded within the regolith, and it requires the 250 degrees to be released, which is higher than the natural environment on the lunar surface. Also above 60 degrees, you have the poles, which has the surface water. Our method will be able to extract that as well. So we can target both potential water supplies on the lunar surface.
Okay. How are you the regolith?
We can discuss that at the table. Yeah, thanks.
So how do you plan to find the areas where you expect to have the Helium 3? Are you just going to be randomly, going across?
No. It wouldn't be commercial if we did that randomly. So the geological report that we've produced is based from samples taken since the first Apollo missions. Mm-hmm. So that's actual, it's actual data from hand-taken samples, not just using spectrometrical imagery, which is a potential for that resource.
So if you're going to be mining this, presumably at the poles, which is where the water is, you're going to be in a very cold environment. What are your power requirements going to be? Yeah,
we're actually targeting around 70 degrees and higher. So one of the things that we're working on now is actually the power supply, which NASA has an option, as well as there's a few other options that you would have seen on the Chinese rover as well, which comes down to cost.
Thank you, Josh.
Thank you very much.